So let's do kind of a quick summary of some quantum mechanical ideas, make sure everybody's good there, and add the concept of quantum numbers. And the concept of quantum numbers is nothing more than just giving like a code name to each of the different orbitals. So our modern atomic theory is called quantum mechanics. The whole problem Bohr really ran into was that he assumed that the electron was a particle, which is a logical conclusion. Protons are particles, neutrons are particles, atoms are particles. He went forward assuming that that's all there was to the story of the electron, when in fact the electron shows what's called wave-particle duality. It basically means that if you set up an experiment to show that an electron is a particle, you win. It will be. And if you set up an experiment to prove that the electron is a wave, you win again. It will be. But an electron is neither a wave nor a particle. It's a thing that we cannot fathom that exhibits what's called wave-particle duality. All scientists know for sure about the electron is that it is not a particle moving in a wavy motion, which is where most people go when you start talking wave-particle duality. Everybody's like, yes, I've got the problem solved. It's just a particle, and every place it goes there in a wavy motion. But we're certain that that's not the answer either. So unfortunately, we have to settle for, we don't know what the electron is. But let's go ahead and try to build a model of the atom to describe what it's doing, even though we don't really know what it is. And Erwin Schrödinger came up with an equation that mathematically calculated the probability of finding an electron in a particular volume of space. And it's kind of a yucky equation, but there are parts and pieces of this that you can make sense of. Second derivative, some of you that kind of makes your blood run cold at this point, of psi, and this is the wave function of the electron. But think of a wave function as nothing more than a mathematical expression, like a function, like math class. So that part deals with the wave component of electron behavior, is equal to 2 times the mass of the electron. So that acknowledges the particle properties of the electron, divided by a constant of h bar. Strangely enough, my computer couldn't put the bar over that h, which is just another one of those fundamental constants, so just a number, is equal to, multiplied by the kinetic energy of the electron, because it is moving, so it has kinetic energy, minus the potential energy of the electron. But that potential energy is a function of how far away it gets from the nucleus, because how much it's attracted to the nucleus depends upon how far away it is, times the wave function with respect to its x position has to be equal to 0. You will not, under my guidance, have to solve this equation. If you are getting a major in chemistry and you have to take physical chemistry, P-Chem as a junior, you will, under somebody else's direction, solve this equation. Here's what you have to understand about this equation. Bohr knew that the electron was quantized. It could only have certain special energies. And Bohr couldn't come up with any reason why that had to be the case. This has got to be true because of the spectrum, but he couldn't come up with a reason why. But this equation does give us some understanding of that. Let's go really simple. Let's say you have the expression 2x squared minus 8 equals 0. What can x be?
2 or negative
2 or negative 2. It can be positive 2 or minus 2. Here's all you need to understand about Schrödinger's equation. If you have an equation that's equal to 0, there are a limited number of correct answers. The allowed energies for the electron are the things that make this true. Just like the allowed values for x are the things that make this true. That's all you need to understand about Schrödinger's equation. we finally had a reason why the electron couldn't have just any energy. It had to have only the energies that made this statement true. So we have now a reason that the electrons are quantized. Okay, so we don't have to solve it, we just have to understand the results. Electrons are mathematically restricted to only certain special energies, and we're going to have to give up on knowing the exact energy of the electron, or we're going to have to settle for knowing the energy of the electron and give up knowing the exact position. Werner Heisenberg came forward and sort of helped this along by pointing out that sometimes you can't know all the things you want to know. And he said it was impossible to know both the position and the energy of the electron at the same time. And the reason was that through the process of measuring things, sometimes you screw up the thing you're trying to measure. I think the easiest way to understand this is to think about a cup of coffee. Let's say I bring a cup of coffee into my room and I set it down and I say, what's the temperature of the coffee? What might you ask for? Yeah, you might ask to borrow a temperature probe. So you plug the temperature probe into your computer, you drop it into the cup of coffee, and what just happened to the temperature of the coffee when you put the temperature probe in? You cooled it down. Or if it's iced coffee, you warmed it up. Okay. The sheer act of measuring the temperature screwed up what the temperature was before you measured it. Because an electron is so small, trying to measure its position, which is something we would do by bouncing something off of the electron, actually bounces the electron to a new location, and we will never know where it actually is at any moment in time. So we accept that we're never going to know where it is, and we settle for knowing its energy, because you can either know the energy or the position, and the energy is related to the spectrum, which is the data we have. So in the end, what we decide to settle for is having an electron cloud, a region of space where the electron could be, and defining an orbital to be 90% of the places that it could be, or where it is most likely to be 90% of the time. So the various steps involved would be input this into computer, ask computer to solve this, have computer make plot of solved thing with X number of dots, and then finding a shape that picks up 90% of the little dots that the computer had. An orbital is a three-dimensional region where the electron will probably be 90% of the time. It's not a path. We're not trying to say how it's moving around in there, because it isn't even necessarily the kind of thing that you can think about. So we don't try to describe how it's moving. Just 90% of the time, you'll find it there. The thing is, 10% of the time, it might not be there. But we've kind of hedged our bets. Like, well, you know, it'll probably be there 90% of the time. If you don't find it there, not really my fault. Okay? We can put up to 2 electrons per orbital. They're designated by a letter and a shape, and they work a little bit like shoe sizes. Like a 1s orbital and a 2s orbital look the same, but the size 2s orbital is bigger than the size 1s orbital. Okay, so if you go in the shoe store and you say, can I try on those shoes in a size 6, 7, and 8? Someone's going to bring you shoes that look identical, a small pair, a medium pair, and a big pair. These orbitals happen to have a variety of shapes. We didn't pick the shapes. They're the shapes that we get when you solve Schrodinger's equation. S orbitals are spherical. They come in sets of 1, and at 2 electrons per orbital, you can have 2 electrons in the S sublevel. P orbitals come in sets of 3. Each of the P orbitals looks kind of like 2 balloons tied together at the neck. I'd make them, but we packed the balloons already. And if the P sublevel has 3 orbitals, that means it can house 6 electrons. And the P sublevel is the combination of putting this and this all on the same point. So it's like one oriented in the X direction, one in the Y direction, and one in the Z direction. The D orbitals get really interesting. They make me think of breakfast. They look like eggs and donuts to me.
Yes.
They come in a group of 5 with a capacity of 10 electrons. And the f orbitals just look like mutated Ds. There are 7 of them for an electron capacity of 14 in the f sublevel. We've talked about why they named them S, P, D, and F, that it represents sharp, principal, diffuse, and fundamental in honor of Bohr and the regions of the hydrogen spectrum. The number of orbitals in a sublevel are just your odd numbers, 1, 3, 5, and 7. And if you know there's 2 electrons per orbital, you can figure out how many in each sublevel. What this means is that Bohr wasn't as wrong as what we thought. Bohr said we could calculate the electron capacity of an energy level by doing 2n squared. So the first energy level, you square 1, multiply it by 2, and you've got 2. The second energy level, you square 2, multiply it by 2, and you have 8. So we get things like 2, 8, 18, 32, and so on. Where Bohr went wrong was his assumption that at the second energy level, all 8 of these electrons were the same. They aren't. There are 2 electrons in the 2s sublevel, 6 electrons in the 2p sublevel, so it's 8 electrons, but of 2 different varieties. And at the third energy level, yeah, we can have 18 electrons, but they come in 3 different varieties. So if the fourth energy level has the 4s, 4p, 4d, and 4f, if we follow the overall pattern here that the number of sublevels is equal to the energy level, that must mean that the 5th energy level consists of the 5s, the 5p, the 5d, the 5f, and some other sublevel. Starting here, they start to go in alphabetical order. The 5g sublevel. But now we have to get a little bit smart. How many g orbitals would there be in a g sublevel? 9. 1, 3, 5, 7, 9. So how many electrons could be housed in the g sublevel? 18. And so now if we do 2 plus 6 plus 10 plus 14 plus what we've now decided should be 18, we get 50, which is in fact 2n squared, just like Bohr said. We really never talk about the g orbitals because to do all 118 elements that we have, we don't need to put anything into the g orbitals. Electrons can jump into a g orbital and fall back and emit energy, but in the ground state, we don't need the g orbitals. However, I just kind of wanted to show you the pattern that beyond F, we just go in alphabetical order to name the orbitals. You learned to put electrons into energy level diagrams, which showed these in order from least energetic to most energetic. You've hopefully seen the box diagrams. So here would be the 1s. Here would be, whoops, 1 up, 1 down. Here would be the 2s. And then the 2p sublevel, because it has 3 orbitals, would look like that. And when we start to fill them for orbitals at the same sublevel, we do it fair. 1 for you, 1 for you, 1 for you. And then we come back and we do 2 for you, 2 for you. And then maybe if I'm out of electrons, I would stop there. The box diagrams are just a quicker, easier way to show this. This one's nice because it gets at the idea of low energy and high energy. And we see what Bohr told us, that they would get closer and closer and closer in energy as you went up. I tend to get a little lazy about my box diagrams, and they start to look like this. You'll even notice that my arrows start to lose half their arrowhead. So my box diagrams sometimes come out looking more like that. In shorthand, we can do the electron configuration if you don't want to draw the pictures. 1s2, 2s2, 2p5. And so the electron configuration was just a way to make a list of where the electrons are. When we fill up the energy level diagrams, we follow 3 rules, which basically say, start at the bottom and work your way up. 2 electrons per orbital, 1 of them spin up, 1 of them spin down, and be fair. So for orbitals at the same energy, give everybody 1 before anybody gets 2. It's sort of like putting kids into bedrooms at your house. You don't dump them all in the same bedroom because they'll fight with one another. You go, okay, 1 of you in here, 1 of you in here, 1 of you in here. And then when the 4th kid comes along, you're like, well, all right, you're going to have to double up now. You learned about valence shell, which is the highest energy level containing electrons. And you did a little bit with ions. Now, I do want to pause here and do a few energy level diagrams for some positive and negative ions. So let's fill in a couple of these energy level diagrams. Let's start by doing oxygen. Oxygen has 8 electrons. So if we want to fill in the energy level diagram, we do 1 up, 1 down in the 1s sublevel. 1 up, 1 down in the 2s sublevel. And now we get to the 2p sublevel and we have to be fair. 1 for you, 1 for you, 1 for you. 1, 2, 3, 4, 5, 6, 7. Okay, so we got 7 electrons so far. And the 8th one has to double up. Okay, so if I drew the 2p better so that you could see it, we'd have an up, and up, and up, and a down. Now, if we change this to make the oxide ion O2 minus, that's easy enough. We need 10 electrons. And we put in the first 8 just like they were before. So there's the 8 I had originally. If you need to make negative ions, you just keep going. I have to put in 2 more electrons. Junk, 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 junk. And I've made oxide. So making a negative ion is relatively simple. Positive ions, however, are a little bit more difficult. With positive ions, we put all the electrons in, and then we remove them, but we start from the highest energy sublevels, and we come downward. So let's do iron. So we'll start by making an iron atom. Iron is element number 26. So we need 26 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So notice I did all the ups, then all the downs. 11, 12, 13, 14, 15, 16, 17, 18. So again, I did all the ups first, and then the downs. 19, 20. So I'm up through the 4s. I got to get to 26. I'm going to give everybody an up, 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 up. And my 26th electron creates a buddy in one of those. So So again, because it can be kind of hard to see, I'm going to redraw the 3D here for you. So we have an up, 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 and one down. It's kind of zoomed in on the 3D. If I want to change the game here and do Fe3 positive, I'm actually going to have you get a pencil and fill this in first for iron. So with a pencil, I want you to put the 26 electrons in. So do iron first instead of iron 3 plus. 1, 2. So to get from iron to iron 3 positive, we have to remove 3 electrons to bring us down to 23. But notice up here it says take your valence electrons out first, then work your way down from the highest energy sublevels. The valence electrons are the ones with the highest N level. So they're these that are in the 4th energy level. The valence electrons are farther away from the nucleus than any of the other ones. So when it's time to lose, the ones farthest from the nucleus get lost first. So to make the iron 3 positive ion, the first 2 electrons out are the 4s. Even though they weren't the last ones in, they're the valence electrons, so they go out first. So 2 electrons out of the 4s sublevel. Then I've got to work my way down from the 3d sublevel. So I got to take one more out. What's the logical one to take? The down arrow. Yeah. If we're going to take one of these out, the logical one to take out is the down, so that we're back to having 1 electron in each of the d orbitals. So the electron configuration for Fe3 positive is 1s2, 2s2, 2p6, 3s2, 3p6. There's nothing left in the 4s sublevel, so you can either write 4s0 or not do anything, and then 3d5. So negative ions, easy enough to make. Positives, you really have to fill up the whole thing first and then pluck your valence electrons out. You learn to manage the diagonal rule. If you are dependent upon the diagonal rule, which some of you have figured out other ways, but some of you like the diagonal rule, you do need to know how to draw this thing for your test. To get it drawn, you write the numbers 1 through 8. And those represent 8 energy levels. Put in the S's. And then just remember it's diagonal. Chop 1 from the start and 1 from the end. 1 from the start, 1 from the end. 1 from the start and 1 from the end to create a diagonal effect like that. And then you just throw in your arrows. And that's going to allow you to write your electron configurations without having to fill up the energy level diagram first.
Do we even need the last diagonal level?
You don't. It makes the diagonal rule neat and clean and easy to draw, however. You really don't need this piece, but if I'm teaching people to draw it and I let them chop 1 from each end on every single column, it makes it easier for people to draw. And that is when the 8s electrons would fill. It would be right after the 7p. Element number 119 actually would go underneath element 87 in the periodic table. So it actually is the proper thing. So you're covered for a bonus 2 elements in the future. And some of you have figured out that you can write the electron configurations just read off the periodic table. 1s2, 2s2, 2p6, 3s2, 3p6. So you just come across 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1 through 10, 4p6, and so on and so forth, where the row number gives you the valence shell and the column number tells you what the electron configuration will end in. You learned about shorthand electron configurations going relative to the noble gases. Like that was a quick whirlwind tour. And then there were a couple things that didn't really come up as part of digital learning. The octet rule is the rule that says that an atom or ion with 8 electrons in the valence shell is relatively stable. Essentially, your main group elements ionize in order to give an S2P6 configuration at the end of the electron configuration. So if we look back to what we did to oxygen, oxygen makes a -2 ion because it needs 2 more electrons to have an electron configuration that ends 2s2, 2p6. We're constantly trying to get to an S2p6 conformation when we form ions, and that's the octet rule. Noble gases already have that, so they're fairly non-reactive. Other atoms form ions to try to get to the same electron configuration with the noble gases. There are, however, other kind of second best situations. So when you look at an electron configuration and try to decide if it's stable or not, 8 electrons in the valence shell is the best. But we do have little blips of stability when electron configurations end with a full sublevel, like S2. For example, magnesium is a little more stable than sodium because magnesium ends S2, but sodium ends S1. P6, but if it ends P6, it actually falls into the octet rule. D10 and F14. So configurations that end like that are kind of good. So octet is best. Second best is ending in a full sublevel. Our next best configurations are the S2 or the S1s, the P3s, the D5s, and the F7s, with special emphasis on D10 and D5. D10 metals and D5 metals are very good, so much so that you end up with some exceptions to the diagonal rule in the areas near D10 and D5. The least stable electron configuration is none of the above. There are some exceptions to the diagonal rule when you're making electron configurations, and they generally occur because of the D5s and the D10s. Exceptions to the diagonal rule occur never in the tall columns. Okay. So the 8 tall columns, they follow the diagonal rule very, very well. If you're dealing with the transition metals, start with the diagonal rule, but then check with the periodic table to confirm the electron configuration if you're looking at a D block or an F block element. So if we look back here, I've actually given you a periodic table. I just copied this out of your textbook. This periodic table shows the actual electron configurations. So something like chromium ends up not doing what you would think it would do. If you were to predict the electron configuration for chromium, and I'll just do it right down here in shorthand. So shorthand, I would back up to the previous noble gas, which is argon. And that counts for the first 18 electrons. I need to pick back up at the 4s sublevel. So I would expect it to be 4s2, 1, 2, 3, 4, 3d4. That's what I expect. In actual fact, the electron configuration for chromium ends up being 4s1, 3d5. Because d4 is so close to d5 that one electron from the 4s sublevel hops up into the 3d sublevel, leaving me with instead nothing special, a half-filled 4s and a half-filled 3d. Now, how are you going to know when this happens? Well, you're going to be on the lookout if your configuration ends very close to d5 and very close to d10. And if we look for things that are exceptions here, here's one that should be a d9, but it's a d10. Here's one that should be a d9, but it's a d10. Here's one that should be a d8, but it's in fact a d9 with both electrons promoted upward. Here's one that's an exception. You don't have to, and you can go through the F block and the D block and you can find all sorts of exceptions. You don't need to know specifically which ones are the exceptions. But I could ask you a question like, chromium is a relatively stable transition metal. Which of these two electron configurations is more likely the electron configuration? And I would expect you to pick the D5 because D5 is a better configuration than D4. But on the whole, our approach is going to be make no exceptions in the tall columns, start with the diagonal rule, and if you need to confirm the electron configuration for the D block and the F block, look at the little periodic table there and just do a quick confirmation. Okay. Last idea related to configurations before we switch to quantum numbers is the idea of paramagnetic and diamagnetic and ferromagnetic. Because electrons are spinning charged particles, they have magnetic fields. A substance that has a bunch of unpaired electrons, they're all spinning and creating magnetic fields that don't cancel one another. So a paramagnetic substance is attracted to a magnet. A diamagnetic substance, for every electron going this way, it has one that goes the other way, and the magnetic fields cancel one another, and it's not attracted to the magnet. It's actually repelled very slightly, but I tend to ignore that because that's not as significant as just knowing if it's got paired electrons, those magnetic fields cancel one another. Paramagnetic means it is attracted to a magnet. Ferromagnetic means that we've used a magnetic field to line all these electrons up to go the same direction, and it is a magnet. So this is attracted to a magnet. This is a magnet. And that's why it becomes important. Things like distributing these one up before anybody gets a down. Because oxygen, it turns out, is paramagnetic because it has two unpaired electrons. Or when we do this iron, to pull the two electrons out of the 4s sublevel, because then we see why iron makes excellent magnets. It has 5 unpaired electrons. You get those all go in the same direction, and you can create a pretty strong magnet. Okay, so that was a review of some things. Here is something a little different. There is an address or a code for each one of the orbitals. And there is a set of 3 numbers, that are needed to solve Schrodinger's equation in 3 dimensions. Those 3 numbers are called the quantum numbers, and it's these 3 right here. You're familiar already with the principal quantum number, n. It tells you which energy level. Its allowed values are like 1, 2, 3, 4. Okay, so its allowed values are 1, 2, 3, and so on and so forth. The next quantum number is the quantum number L. And it's always, for some reason, drawn with a cursive L. It's called the angular momentum quantum number, but I can't think that you're ever going to need to know that. It tells you which sublevel. And its allowed values are 0, 1, ... all the way up through n minus 1. Now this is going to be really confusing just for a couple minutes, and then we're going to straighten out the mess. Then there is a magnetic quantum number, m sub L. And it tells you which orbital. And its allowed values are negative L up through 0 and onward to positive L. And those are the numbers needed to solve Schrodinger's equation. If we revisit Pauli's exclusion principle, that was the one that said electrons can live together if one is spin up and one is spin down. Rephrased, Pauli's exclusion principle says no 2 electrons in an atom can have the same quantum numbers. And so Pauli added a 4th quantum number, m sub s, which can be plus 1/2 or minus 1/2, and that's it. Okay, now that's a confusing mess. Here's a better, easier way to think of it. N tells you which energy level. That one nobody ever has problems with. L tells you which sublevel. Here's the code. The S sublevel has an L value of 0. The P has an L value of 1. D has an L value of 2. F has an L value of 3. So if we try to make sense of this, let's go down here and say, I've got the 3rd energy level. That means N equals 3 for the 3rd energy level. And the rule for L is that it starts at 0 and it can get as big as n minus 1. So the allowed values for L in the 3rd energy level are 0, 1, and 2, because n minus 1 is 2. And L being equal to 0, 1, and 2 represents the 3s orbital, or the 3s sublevel, the 3p sublevel, and the 3d sublevel. So n equals 3 L equals 2 is code for the 3D sublevel. For each of the L values, you can then have M sub L values that range from negative L up to positive L. So we're going to have to come down now from each of these L values. If L equals 0, M sub L equals 0 as well, and that's it. If L equals 1, M sub L can be negative 1 or 0 or 1. And if L equals 2, M sub L can go from negative 2, or it can be negative 2, negative 1, 0, 1, or 2. And suddenly I think this will be better. How many s orbitals are in an s sublevel? Just one. And that's why M sub L only has one answer to the which orbital. How many orbitals at the p sublevel? 3. And that's why there's 3 of them, negative 1, 0, and 1. How many orbitals at a d sublevel? 5. Negative 2, negative 1, 0, 1, and 2. We're basically just assigning a number to each of the orbitals in the sublevel. And within here, I'll show you got another color. The s orbital can have one electron that's plus 1/2, and its second electron has an m sub s of minus 1/2. Okay. And here in the negative 1 orbital, we can have a plus 1/2 and a minus 1/2, and in the 0, we can have a plus 1/2 and a minus 1/2. And you eventually end up at the point of having 6 electrons here and having 10 electrons there. I created this. I call it Dorner's colorful grid of quantum numbers because I think it makes the most sense this way. The first energy level consists of only an s sublevel. That s sublevel is 1, 0, 0. That's its code. The second energy level can have an L value of 0 or an L value of 1. If the L value is 0, M sub L is it's automatically 0, and we're talking about the 2s sublevel. If L is 1, we're ranging from negative 1 all the way up to 1, which accounts for the p sublevel on the x-axis, the p sublevel on the y, and the p sublevel on the z. And at the third energy level, you can have 0, 1, or 2, and then you can figure out your M sub L levels, and you can see all of the orbitals in the third energy level and the fourth energy level. And so at least for me, this kind of laid it out so that I could actually understand why the values were what they were. Why it had to be that M sub L went from negative L through 0 and up to positive L. Well, it's because if this is 3, that creates 7 values. And those values can represent the 7 orbitals in the F sublevel. Okay. Now, quantum mechanics is kind of hard and kind of weird and kind of miserable. But in the end, you don't have to really understand it. In fact, you can't understand it. I think my research advisor in grad school hit it on the head when he said, the first time you take quantum mechanics or learn quantum mechanics, you think, yes, I've got it. I totally understand this. And the second time you take quantum mechanics, you think to yourself, or no, what was it? The first time you think, I really don't understand this. And you're right. And the second time you take it, you're like, yes, I've got it. I really understand this. And you're wrong. And the third time you encounter quantum mechanics, you think to yourself, I don't think I really understand this. And for the first time ever, you're right. When you realize that you cannot understand this because you don't know what the electron is, that's the point at which you really understand quantum mechanics. What we can do is learn to use it. You can use the diagonal rule and write an electron configuration. You can fill up an energy level diagram. You can look at the energy level diagram and decide if there are unpaired electrons or not and predict whether it's going to be paramagnetic or diamagnetic. you can use the quantum numbers to write the address system for a particular electron. Those are the things that you need to be able to do with the quantum mechanics. Okay, I think what I'm going to do is stop there for the day, and I'm actually going to real quick print some paramagnetic diamagnetic practice for you, because in 15 minutes I really don't think we can make meaningful headway into the next thing we need to do. So I think maybe the thing to do would be to have you do a little bit of practice with paramagnetic and diamagnetic. So I'm going to print that real quick and